Okay. Can you all hear me okay? This is going to be the second hour of Physics 1A for May 10th. Okay. Yeah, can you all hear me okay? Is everything working fine? Okay, I see people typing, so we're probably good. All right, so the last thing we wanted to do, finishing up from the previous part, is to find the initial force of the pivot. So can I take... Let's see if I can take most of this. Copy it down here. Come on. All right, we can get rid of this. Okay, now one of the things that we calculated in a previous part we're also going to need is the definition, or this right here. So let's grab that as well. Okay, so now we want to find what the force is on the pivot right here. I guess before we even do this, in the previous part, we calculated the force on the pivot when the rod was vertical. And we're now going to calculate the force on the pivot in this situation. I guess the first thing to ask, what do you all think the answer is going to be? Do you think it's going to be greater than this? Do you think it's going to be the same as this number? Do you think it's going to be less than this number? Do you think the force on the pivot at the beginning is bigger than or smaller than the force when it gets to the vertical position? Just take a guess. Thinking less? Think it's going to be the same? Bigger maybe. Okay. All right. So let's calculate it. Sorry, my pen. Oops. Here we go. Okay. So what can we even do to solve for what this force is going to be? How would we go about doing that? Any ideas? We're going to have to do sum of torques, you think? And the problem with doing sum of torques excuse me, is that the natural place to sum the torques is right here at the end. And there's not any torque from the pivot force on this end right here. Yeah, you can't really solve for P. So we have to do something else. What else could we do? We're trying to find a force, so we don't really... There's not many options as to how we... Like equations that have forces in them. You know what I mean? What equations do we know that involve... Yeah, that's all we can do. Sum of forces. That's all we can do. That's right, Kelvin. So we're going to do the sum of the forces acting in the y direction. This is still the y direction, positive y direction. Should be equal to, again, we can use the total mass of our system, which is m plus big M. And we can basically use the same equation we used in the last part. We can just say, if I sum all the forces in the y direction, that should be equal to the total mass times the acceleration of the center of mass of the system. If you look back, this is the same equation we just used, right here. Except in part D, the system was rotating and had radial acceleration. In this case, that's not going to be happening. Now the acceleration of the center of mass is just going to be, well, it's kind of similar, because what we're going to do is we're going to say, we know what the angular acceleration is initially, and we can relate the acceleration of the center of mass to the angular acceleration by using this equation. Basically, A is equal to r times alpha. So for us, we're going to say the acceleration of the center of mass of this system is going to be equal to the center of mass distance from the pivot multiplied by alpha initial. But really, this equation is just A equal to r alpha. This is how we relate linear acceleration to angular acceleration. Okay, but that's kind of the version of it we're going to use here. Because now the center of mass is accelerating, but it's accelerating downwards initially. This is the direction of the acceleration of the center of mass. Okay. So, putting all those things together, sum of forces in the y direction on the left hand. Oh, I said a lot of stuff there. Does anyone have any questions? So on the left-hand side, we have sum of forces in the y direction, which are P minus little mg minus big mg equals m plus m. And then we replace ACM, the acceleration of the center of mass, with the coordinate of the center of the mass multiplied by alpha initial. And then we just solve for P. Probably going to run out of space here. P equals... we're going to have mg plus big mg plus m plus m times RCM times alpha initial. And we know what all these things are, so we can plug them all in. We'll just go to the left right here. So little m was 0.36. Plus big M is 0.1. Times gravity plus RCM, which is 0.609. We calculated that in the previous part, times alpha I, which was 12.5. And that should all be equal to P. I did the same thing as I did in the previous part, which is I noticed that M and M plus M appear in both of these, so we factor that all the way out to the front. So all of that multiplied by all of that. And come back to here. We're going to get this over here. So again, tying this back to the first question that I asked here, I asked you all to think about, well, is the answer going to be bigger than or smaller than what we got before? So in the vertical situation, we got 11.5. And so this one, if you guessed smaller, you were right. So good job if you did. If you didn't, that's okay. The whole point of this is just to get you to think about what it should be. I think it makes sense that the force would be bigger when it's vertical, because now the pivot force has to do basically three things. It has to support each of these weights, right? And it also has to support the fact that the rod is swinging, which means it has circular motion, which means radial acceleration. So that's going to make it so that this force has to kind of, overcome all that stuff. Whereas here, when the rod is vertical, the force P just needs to kind of, it has to be big enough, but these two forces are still going down opposite to it, but the acceleration vector is pointing in the opposite direction now. Like it's going down, which is opposite this one, right? Actually, looking at this, I think I did something wrong here, didn't I? Yeah, well, is it going to change the answer? I think it does change the answer. Because the acceleration of the center of mass goes downwards, right? Which means I should have made that direction positive to be consistent with the way that I've taught you all to do this stuff. So if this is the direction of the acceleration of the center of mass, then I need to make that direction positive y, which means I need to make this negative, this positive, and this positive, which means when we solve this, I think that this is going to be negative right here. I think this piece right here should have ended up being negative. Right? Do you all agree? I'll put it in red so I can indicate what I changed. Does that look right now? I thought this number was too big, because I think the answer is supposed to be like 1. So if I go back to here and I do this same equation again, and I put a minus sign right here, yeah, 1. That's what I thought the answer was. Okay. Sorry about that. 1 Newton is the answer here. Okay, did you all see the change that I made there and why I made it? Basically just switched the direction that I called positive, which meant that P is now negative and mg and mg are positive. And the right-hand side stays the same. This doesn't change. But it does give us a smaller answer here. Do you all understand? No one's saying anything, which makes it really hard for me to continue, because it makes it feel like I didn't explain this well enough. So, can anyone ask a question so I can help clarify, or? Okay, I can answer both those questions. So here's our equation that says P is equal to, I'll do this in 2 steps. The first term here is m plus m times g minus m plus m times RCM times alpha initial. And then we can factor m plus m out of here. So it's m plus m times g minus RCM times alpha. Can you see that now? Then how this becomes this? Yeah. One thing that I'm more than always happy to like add these steps in here, but part of the reason why I do this is because you're going to notice as you go on to like a 4-year school where you have less time in lecture, your teachers are going to skip more and more steps basically, and kind of expect that you can kind of work it out yourself. So you have to kind of start getting used to just kind of working the steps out. Again, in this setting, I'm more than happy to explain it, but I mean, I can see why it's not easy to see. I totally understand. Why did I change y downward to positive? So it's because all three of these vectors right here are going down, and the way that I do Newton's second law problems, in order to try to not make any mistakes, is when possible, I try to take the direction of the acceleration to be positive. Maybe the right way to say it is the direction of motion is what I'm taking to be positive, but in the past I've always said direction of the acceleration to be positive, although I saw a problem recently where maybe that's not the right way to say it. It might be the direction of motion is what I need to take, is what I need to make positive. But that's the reason I'm giving, and I'm not sure. Again, this is the way that I learned it for years, and I only recently saw something where it made me question it. But I always, in every problem we've ever done in this class, I always look at the direction the object's accelerating. So in this case, it's accelerating down, and I make that the positive y direction. That's always been the way that we've done problems in this class. Is pick the direction of the acceleration to be positive. So that's why I had to switch the direction here. Because it isn't accelerating up. So, I mean, it is accelerating down, so I want to make this positive y down. Does that make sense? Yeah. It's just like the problems that we've done in the past where you have like... I'm kind of over-explaining at this point. You have like a mass here, and it's connected by a pulley to another mass right here. It's how like... we use this positive direction for this one, but this is the positive direction for this one. That's basically what's going on. And then I think if it was moving the other way, you'd probably switch it. But if it's going that way, that's kind of the idea. Okay, was that? Were there any other questions that anyone had? Okay. Again, to get back to what I was saying, it was 11.5 newtons, the force of the pivot whenever it was vertical. It's 1 newton here, and that's because the pivot doesn't need to support nearly as much of the weight because the system is accelerating. So the pivot doesn't need to support the total weight of these two objects. What would the total weight of those two objects be? It'd be like half a newton, right? 0.36 times plus 0.1 is 0.46. So about 0.5 times 9.8 is about, half a newton. So, yeah. Anyway, okay, so that's a pretty good problem. It's actually a really good problem because it covers just a lot of different things. You're going to see problems like this show up on your homework for sure. And hopefully I've covered most of the details of how you handle them so that you can handle them yourselves when you see them on your homework. Okay, so the next thing we want to do is talk about rolling without slipping. Right, and that's what these next two problems are about, yeah. Okay, so let us discuss that. Okay. So rolling without slipping is going to be a phrase that you're going to see show up in some of the problems that you'll see not only in this class but also in other physics classes. It refers to what I would say is what you normally call rolling. You know, when your tires roll along the road, they tend not to slip. But if you come across like an oil slick or something like that, your tires might slip a little bit. Just like if you're wearing socks and you walk on like a freshly waxed like floor, you might slip as well because you can't get friction. So as long as there's enough friction between the surfaces, then you're going to get rolling without slipping. And again, this is rolling without slipping is what happens when you ride your bicycle, when you drive in your car. It's what you think of as normal rolling. It's rolling that occurs without the wheels or the object slipping in some way as the object moves. So the main criterion here is you need enough friction so that the wheels or whatever you're talking about can actually grip a surface. But when you do, then you can get this rolling without slipping scenario. Now, to describe how this works, let's start off with like a surface. And let's make it like a color that we can see a little better. And then on our surface, let's put like an object like a wheel or a circle that's going to roll. Let's say that this is a disk, okay? And we'll say that it has a radius that we're going to call capital R. And let's say that this disk is rolling along a surface and that it's rolling with an angular speed that we call omega. And we'll also put on here a velocity for its center of mass. So we're going to say that its center of mass is going to have velocity, and I'll draw it from the center of the object here. That's going to go this way. So this is going to be the velocity of the center of mass. And we're going to say that this object is rolling without slipping. That means that as it rolls, it's going to push off of the ground at this point right here due to static friction. When something rolls, it's going to be pushing off with static friction. And what we'd like to do is to connect together the velocity of the center of mass with the angular speed. And it turns out that that's really, really easy to do, because let's say that this object rolls through exactly one revolution, okay? So our object starts off like this, and it rolls through exactly one revolution, okay? And it ends up over here, okay? So this is one revolution later. Okay. Now, if it rolls without slipping, that means that as it's rolling across this surface, the bottom piece never like slips as it tries to roll. And that means that the circumference of the object is going to roll out in this direction here. Once it's gone through exactly one revolution, the distance that it's traveled in the x direction, if I call this delta x right here, if it's exactly one revolution and the surface was always in contact with the rim, that means that delta x has to be exactly equal to the circumference of the circle. Does that make sense? Is that consistent with the phrase rolling without slipping? That it should roll through exactly one circumference in one revolution? Can you all see that connection? So the other piece I'm going to say to this is we're going to say let omega be a constant. So this object's not slowing down. And we're going to let the velocity of the center of mass also be a constant, okay? So it's not slowing down, its translational motion and its angular motion are constant, okay? And let's say that the time that it takes to undergo this right here, we're going to call delta t. So delta t is going to be the time interval to go between these points right here, okay? All right. So if that's the case, then I can write the following statement down. Because it's moving with a constant velocity, I can say that delta x divided by delta t is going to be equal to the velocity of the center of mass of the object. Would you all agree with that statement? That's basically just the definition of velocity, right? If it undergoes a displacement delta x and we divide by the time interval, that gives us the velocity of the center of mass. But delta x, we said, was equal to 2 pi r. So I can write this like this. 2 pi divided by delta t multiplied by r is equal to the velocity of the center of mass. And then the last thing that we can do is we can say, well, 2 pi divided by delta t happens to also be equal to its angular speed. Because 2 pi is the amount of angles that it rotated through. One revolution is 2 pi, and the time took was delta t. So we can basically replace this entire thing with just the angular speed omega, and it gives us this relationship. The velocity of the center of mass of the object is equal to the angular speed of the object multiplied by its radius. This is a really simple relationship, and this is basically one of the two conditions for rolling without slipping. The other condition is that you can get a similar connection between the angular acceleration of an object and the acceleration of its center of mass when it's rolling without slipping. Now, we actually used this relationship in the last problem, but it just happens to be the same relationship that you get when you talk about tangential motion. So rolling without slipping has these two equations, not to be confused with the other two equations that look exactly the same. Right? See how these equations are exactly the same, but they basically correspond to different things? It's nice because it's the same equation each time. It's just v equal to r omega, but they mean different things, so you got to be kind of careful. With rolling without slipping, what we mean by the velocity here is the velocity of the center of mass. Oh yeah, you can't see this piece right here, right? Sorry, these are the other two equations. Tangential velocity is equal to r omega, and acceleration tangential is equal to r alpha. These equations are used when you have situations like the problem we did with like the pulley with the mass on the end, and we said that the tangential acceleration was this way, and the angular acceleration was this way. And then we said, well, now we can write a tangential is equal to r times alpha, right? So I just want to, like, the equations, they look the same, but it's just like, it's used for something different, and they mean something different, right? So you need to be able to kind of distinguish between them. So for rolling without slipping, you have these equations, which relate the velocity of the center of mass of the object to the angular speed of the object to the radius. And same thing for the acceleration of the center of mass if the object's accelerating, and the angular acceleration and the radius of the object. Anyway, so these are the conditions for rolling without slipping, and you're going to have to use them in any problem where an object is both rolling and slipping. Okay? You have any questions? So let us look at a problem that we can use these concepts to solve. This is a very common problem that shows up in pretty much every single physics textbook because it's just a really good problem. So this is like a it's like kind of like a roller coaster kind of problem, I guess. So what you have is we have a it doesn't say. Oh, it says ball. Okay. So it says find the minimum height h min in terms of r. R is the radius here. That will allow a ball to roll around the loop without slipping or falling off. So we want to figure out the minimum height here so that we can release a ball from rest so that it rolls down this way and can roll all the way around this loop without falling off at the top. Okay? That's our goal. Find this minimum height right here. Does the problem make sense? So the other thing we're going to do, because this is going to show up in your lab manual problems too, is we're also going to calculate what the acceleration of the ball is when it gets to this point right here. The radial and the tangential acceleration of the object when it gets to this point right here. That's the second thing we're going to do because that's going to show up in your homework questions. So I want to make sure that we've covered that. Okay, so let's get to it. All right, so we want to find the minimum height here that will allow the ball to roll around the loop without slipping or falling off. So the ball starts from rest, so we know it has an initial velocity of 0. And when it gets to this point right here, we actually know something about its velocity at this point, don't we? Does anyone remember what we learned early on? Not early on, but when we started talking about circular motion, about objects that are going around loop-the-loops like this. We did a problem where there was like a bucket that we were swinging around, and we figured out what the velocity of the water at the top was. What do we know about the velocity of this object at the top up here? What does it need to be if it wants to be able to roll around the loop without slipping or falling off? That's right. So I'm going to call this, I think we can call it V final. I think that's fine. And this needs to be equal to r times g square root. Right? That's the, so I'll write it up here. So VF equal to square root of r times g. This represents the minimum velocity at the top so that the ball doesn't leave the track, basically. Or just barely leaves the track is basically what it is. But okay. And we went through this derivation in a previous class. It's not hard to do. You basically just, you set the centripetal acceleration equal to gravity at this point, and you get this answer. Okay, so we know what the velocity here needs to be. We also know the initial velocity. Now we need to start taking into account a couple other things right here. So we also know the final height, so to speak. So what I'm going to do is I'm going to define this position right here to be y equal to 0. And that means that this position right here is going to be what we call y final. And it's going to be equal to 2 times r, because it's the radius from here to here is 1r and then 2r up to here. And for y initial up here, we don't know what that's equal to. That's what we're trying to solve for in the problem, the minimum height, right? So we'll just put a little question mark right here, but basically this is what y initial is equal to, this h min. And that's what we're solving for. Okay, now, what type of equation do you think we'll use to solve for this problem? What's the best, when you look at this, what does it tell you? What kind of equation would you want to use to solve this type of system? Probably energy, yeah. What is it about the problem that lets you know that it's energy? You're right, it is. We're going to use energy. Heights, okay, that's kind of an answer. It's not the best answer. What's the difference between a problem where you have an object like a block going down a ramp and a block going down a ramp like this? So 2 objects, you get an initial height. No, it's not because rolling's involved. I'm asking between these two. So I give you a problem with a straight incline, and I put a block on it and ask you, how do you solve this problem? There are multiple answers. There's ways you can solve, like suppose your goal was just to find what is the velocity of the object as it gets off the end right here. That's your goal, okay? It's because it's circular, yeah. It's because the path is curved. That's why you have to use energy, because the path is curved. Let's go back to the first question we did today. Why did we have to use energy in this case? It's because the path's curved, right? It's a curved path, which meant that the acceleration was not constant, which means you can't use kinematic equations, right? If I give you a problem with a flat incline and tell you the height that the object starts on the incline, and I tell you what the angle is, you could find the final velocity by using kinematics, because this object's going to move down the ramp at a constant speed that you can figure out, or not a constant speed, but a constant acceleration that you can figure out using Newton's laws. But when I have an object that goes along a curved path, that's a big sign that energy is going to be the best way to handle it, because it's guaranteed to have non-constant accelerations. Okay, so curvy path, use energy. If you see a spring in a problem, you should use energy, similar kind of thing. Okay, so we have initial velocity equal to 0. We have all the information we need, but there's actually there's 2 other pieces of information we're going to need that aren't even written here, but we'll just write our energy equation down, and we'll just figure out what we're missing, okay? Okay, so our energy equation says work done by non-conservative forces is equal to change in kinetic energy plus change in potential energy. There is no spring, so it's just going to be the potential energy due to gravity here. There's no non-conservative forces acting this problem. There's technically friction, though. This is something you're going to have to kind of get used to ignoring, but the whole point for something to roll without slipping, and this is a situation where something is rolling without slipping. There it is. It says it right there. We want to be able to go around the loop without slipping or falling off. The fact that it says without slipping means you need to have enough friction, but you're not going to worry about the energy losses due to friction in these problems. Is that clear to everyone? there is friction in these problems, but we're not going to quantify the energy lost due to friction, basically. Does that make sense? Okay. You're right to be confused about that, and you could say, oh, well, certainly we're making some kind of an error when we do this, and we are. But chances are it's probably a pretty small error, is the idea. And we really don't want these problems to get immensely complicated. Would that be the case even if they make a point of saying there's this... Yeah, if it specifically says and tells you how much energy is lost due to friction, then you can use it. But as you can see in this particular problem, there's really no information about the friction force, right? There's also not really any information about how far we're moving. We don't know what this angle is right here. So we kind of just have to say, okay, well, we don't have that information. We're never going to be able to find that information. I mean, it's a problem. It's just, it's not like a real life situation. But anyway, okay. So worked on my non-conservative forces, delta K plus delta U. Okay, when we're talking about the kinetic energy now, there's now two pieces to this, and we'll have to use both of them now. There's going to be 1/2 mv squared. This is going to be for translation. Plus, remember that this object is rolling now, because it says allows the object to roll. It's not sliding. Because it's rolling, it's also going to have rotational kinetic energy. And then we have to put in here the change in potential right here. Okay. So there's our equation. So the pieces that I didn't have written up here are, there is going to be an omega initial here, which is the initial angular speed of the ball. Since it starts from rest, its initial angular speed is going to be 0. And there is also going to be a final angular speed up here. Now, the trick here is to use the equation that is written above there, which is that the velocity of the center of mass of the object is related to the angular speed of the object through this equation here. That means that on my equation right here, for omega final, I could, if I want to, just write that since the ball has a velocity of its center of mass, that's going to be root rg, the final angular speed would also then just be that velocity divided by the radius. Because that's what the equation says, right? That's how they're related to it, and we derived this. So let's start putting everything together then. So these are 0. It starts from rest, so the initial angular speed is 0. The initial velocity is 0. And we're solving for y initial. So let's write that, let's move that to the left-hand side. So we'll have mg y initial is equal to 1/2 m v final squared plus 1/2. Now what do we do with moment of inertia? If you were given this problem and I didn't tell you what to do, what would you do about the moment of inertia, I? What can we do about that? What do we use for moment of inertia in this problem? So you say you check the charts for the moment of inertia of a sphere. That's the right thing to do, yeah. That's right. So if we go to the book, there's two options. You both put them there, 2/3 and 2/5. So we have to just kind of make a choice. So we're looking at this chapter. Moment of inertia. Okay, so here's the table. Oh, this is the wrong chapter, but it doesn't really matter. So solid sphere, thin spherical shell. Which one should we use? The solid sphere or the thin spherical shell? It just says ball. So if it's like a billiard ball, then we use the solid. If it was like a tennis ball, we use the thin one, right? So we don't really know what it is. So let's say that it's a solid sphere, okay? 2/5, let's say. But it's really kind of, it's ambiguous, right? It's not super clear. So we'll just say that the ball is a solid sphere, okay? And so we're going to use the moment of inertia for this one to be 2/5, right? That's what it was. Almost always the problems you see on your homework are going to be a lot more clear. That being said, okay. Oh, let's be careful about r here, by the way, because r is already the label for the radius of the loop, right? So let's use a different r right here. We'll use little r for the radius of the ball. And actually, I noticed that I made that mistake right here, too. When we define what the angular speed is, this is going to be Vf over little r, where little r is the radius of the ball. Because this radius that shows up in this equation right here, for VCM equal to r omega, is the radius of the object, not the radius of this path that it's traveling on. Okay, so I made this change right here. Omega f should be equal to Vf over little r, where little r is the radius of the ball, in case you didn't see that change. Okay, so going back to our equation, we were doing energy equation, changing kinetic energy. We made the terms that were 0, 0. We took mg times y initial, we moved to the left-hand side. We wrote 1/2 mv final squared, that's that term. The next term was 1/2 I, and we're now saying that we need to plug in here 2/5 multiplied by the mass of our object times the radius of the object squared. And then we have to multiply by omega final. But omega final is equal to v final, which is the velocity of center mass of the ball final at the top, divided by the radius of the ball squared. So basically we use that equation to replace v final in here. Or sorry, to replace the omega final. And one thing will happen when you do this is that these radiuses will cancel, basically. The radius from the moment of inertia and the radius from the angular speed should cancel when you do that. R squared, R squared. Okay, now more things can cancel. Our goal was to find y initial right here. So we can now cancel out masses from every term. Like I said, we can cancel out these r's. And what we're left with is g times y initial is equal to 1/2 v final squared. Oh, I left a term off. Whoops. Plus mg y final. And y final, I believe, was 2r. So we get that. So we have 1/2 vf squared plus 1/2 times 2/5 is 1/5. Everything else canceled, we just have v final squared that shows up here. Plus, and this other mass should have canceled out now too, now that I've added it in. So this times 2gr. And now the last thing to do is to plug in the fact that kind of the first thing we said about this problem was we know that square root of RG is the minimum velocity at the top so the ball doesn't leave the loop. So that has to be, tracking that back to the question. We wanted to find the minimum height in terms of R that will allow the ball to do all this stuff. So since it's minimum height, we correspond that to the minimum speed you need at the top. So everywhere there's a VF now, we can replace it with square root of R times G. So VF squared then, right, is obviously equal to just R times G. So everywhere we see VF squared, we're going to put RG. So we have 1/2 RG plus 1/5 RG plus 2 RG. And all of that's equal to G times Y initial. So our Y initial then is equal to, let's see, 1/2 is 0.5 and 1/5 is 0.2. So 1/2 plus 1/5 is going to be 0.7 plus 2 is going to be 2.7 times the radius. That is our minimum initial height that we need to drop the ball from on the track so that it will actually make the loop without falling off the track. And we actually have a really nice loop-the-loop just like this in the classroom. It's very big. It's very easy to play with and see. And we would actually test to see if this is true. And it generally tends to be a little bit true. It's pretty close to true. You usually have to drop it from a little bit higher than this height because you do have some energy losses due to friction, which are pretty obvious when you roll the ball around the track because you can hear it. You can hear what's really loud. But anyway, actually it's pretty close to the right answer. You need to drop it a little higher than twice the radius. See, twice the radius would be the minimum speed you would need just to get up to this point. But objects won't just automatically climb up to a point like this. They need to have enough speed to actually get around, right? That's why you have to drop it from a little bit more than double the radius. In fact, I think this is a question that I'd asked people to predict what they think the answer was, and some people had said, oh, you think that it's only 2R that you need to drop it from, but you actually have to drop it just a little bit higher to get it to actually go all the way around. Okay, before I add another part of this problem, does anyone have any questions? Did you all solve this problem in your 2A class? Or maybe your high school physics class? Vaguely remember maybe doing something like this? It usually comes up in 2A, yeah. Okay, so the next thing to ask to make this a little bit more tricky is to find if the ball, suppose we use this as our initial height now, right? And we drop a ball from there. What I now want to do is I want to say, what about when the ball gets to this point right here? So the next thing I want to do for this part B, I'll just kind of scroll down and write what I want to do is I want to say, here, let's label this point to be point P. And we want to find the tangential and radial acceleration of the ball at P. Okay? Does that make sense? Okay, so how could we do this? What do we need to do to find the tangential and radial acceleration of the ball at point P? You don't have to answer both at the same time. You could just choose one to answer if you want to. We need to find alpha for a tan. We actually don't in this case, but I know what you're thinking. Use energy equations. We're definitely going to have to do that. Okay, what I'm going to say is that let's not worry about this one for now. Let's just do this one, And then we're actually going to do another problem that's going to help us to solve this part. This part's actually this is, finding the tangential acceleration is actually quite tricky. Finding the radial acceleration is actually not that hard. Okay, so to find the radial acceleration, Andrew's saying use energy equations. What do we use the energy equations to find? What do we need to know? If I want to find the radial acceleration of the ball at this point right here, what do I need to know about the ball? I really only need to know one thing. How is radial acceleration defined? What time is it? I need a clock in this room. Force of the ball. Just think about how do we define radial acceleration? Okay, that's one way, r times omega squared. What was the other way? Perpendicular force. That's not the answer. It's simpler than that. We also call it centripetal acceleration. V squared over r. That's all we need to know. If I know the velocity of the ball at point P, and we square that and just divide by the radius of the path, that gives you the radial acceleration, right? So we just need to find the velocity of the ball at point P. That's it. And we can use energy for that, right? Because if we find what the velocity of the ball at this point is, then yeah, we can easily just make this calculation, right? Okay, so let's do that, but we need to take a break again. So we'll take a 10-minute break here. Maybe you can try to figure out, calculate that yourselves if you want to, but man, it feels like I feel like when I go slowly enough to make sure that like I give time for you all to ask questions and stuff like that, it just feels like we never do anything. But that's okay, I think. I mean, I think this stuff's kind of tricky, and I think it makes sense to go through it slowly. So, all right, let's take a break until 4:18. And when we come back, we're going to solve this. And then the next thing we're going to do, this wasn't actually something I was planning on doing today, but I think it's actually worthwhile. The next thing we're going to do after this one then is we're going to solve this problem here, because it's going to help us to be able to solve the tangential acceleration part of this problem. Okay, so that is kind of a hint of where we're going next, in case you want to look ahead. Okay, let's take a break.